It's my great pleasure to introduce Eric Horvitz, who's our keynote speaker. Dr. Horvitz is a doctor, having received both an MD and a PhD in biomedical informatics from Stanford University, which he's combined with an extensive career focused on seminal foundational and applied work in AI and data science with a long-standing effort in the healthcare space. He's been working specifically in biomedical and health data science and AI for over 40 years, starting with his dissertation research, which was focused on Bayesian belief network-driven expert systems to interpret pathology slides. So, shout out to the pilot project that was working in that space with very different technologies. Some highlights of his career from a leadership perspective is that he has served as head of Microsoft Research and on the congressionally appointed National Security Commission on AI. Currently, he serves on numerous relevant advisory board, including the National President's Council of Advisors on Science and Technology and the Allen Institute for AI Advisory Board. Currently, he's the Chief Science Officer for Microsoft with a broad portfolio that includes a strong emphasis on the data science and AI space, specifically including the strategic efforts in AI and biomedicine. All of this, I hope you can see, will gives him a unique perspective on the topic of AI in healthcare. And I will turn it over to Eric to trace the arc of AI developments and the directions, possibilities, opportunities, and challenges that lie ahead. Thanks again so much, Eric.
Well, thank you, Peter, and hi everybody. Let me just say that looking forward to meeting people in person in a number of different settings coming up. Well, it's an honor to be here at the 2025 UW Institute for Medical Data Science Symposium, and as Peter mentioned, I'll share some reflections about AI. It's a rising technology with deep implications for healthcare, public health, as well as bioinformatics and the biosciences more broadly. And I'd like to start with an arc through time from the earliest days of AI medicine to where we come today as we talk about the opportunities and frontiers ahead. So, I like to always start with what the heck is AI these days? I like to use the definition. It's the study of computational mechanisms underlying thought and intelligent behavior. The founders of the field in their document in 1956, first written in 1955, was mentioned the goal of trying to find how to make machines solve the kinds of problems now reserved for humans. Now, shortly after that phrase, AI was first used, Robert Ledley and Lee Lusted wrote a really remarkable piece, a remarkably prescient article on the reasoning foundations of medical diagnosis. And they talk about combining symbolic logic and probability and decision theory to aid our understanding of medical reasoning and the prospect of building computing machines that could help physicians with diagnosis and therapy. And these methods really set out a normative basis for reasoning and decision-making, building on the work of von Neumann and Morgenstern, who introduced the axioms of utility in the late 1940s. And it's been taken as that normative basis has been taken as a definition of rational thought and behavior, and is also viewed as a remarkable achievement of the 20th century. Now, about 10 years after that paper, there was progress made with an implementation of some of the core ideas proposed in Ledley and Lusted's classic work, Anthony Gorey and Octo Barnett, where they described a model of sequential diagnosis and they applied it to pediatric cardiology and acute renal failure. Now in the approach, evidence from a patient would be obtained by the system, and it would use a methodology to construct a differential diagnosis, list of diseases by likelihood, make a decision to halt and treat now under uncertainty or the current uncertainty, and if not, to recommend the next findings, tests, or studies to do to gather that information and to cycle that back into the system along with the original evidence to continue to update that differential diagnosis. Now, the whole approach was further explored by numerous teams, including my team, then working with Peter Tarcy-Hornick back in the 1980s, when I was a graduate student at Stanford, where we explored the power of Bayesian networks to do the updating of generating a differential diagnosis, and the power of decision theory to just make decisions about halting versus continuing, and identifying the next best test with the maximal value. And these methods were applied expected value of information as well as Bayesian updating to other domains. The domain that I worked in was a pathology diagnosis. And again, I can say Peter Tarzi-Hornick was a collaborator on this team, as well as trauma care systems and looking at time-critical reasoning. So in late 1990s to today, medical data became available. And this was in part because of the digitalization of medicine, along with the electronic health record. The work, along with advances in machine learning, led to explorations of the use of machine learning to construct diagnostic and predictive models, and to connect these systems directly with hospital information systems to provide predictions based on fixed sets of evidence from the electronic health record that were identified by the machine learning algorithm as the most valuable things to look at. Now, one of the earliest running systems was the one that my team built in collaboration with a team at the Washington Hospital Center, the other Washington in Washington, D.C. It was a MedStar hospital, one of the largest urban hospitals in the nation. We explored several predictions, including readmissions within 30 days after discharge, as well as the risk of the onset of hospital-acquired infections within certain time periods. The work stimulated perhaps one of the first machine learning products that was employed in hospitals throughout the world. This was called the Microsoft's Readmissions Manager, which came out of the research. It would actually, for every patient being discharged, would compute a probability, well-calibrated probability of discharge, leading to a readmission within 48 hours, for example, and also gave a factors pro and against the readmission, kind of an explanation. So machine learning was powerful of the classical form in that it could provide well-characterized predictions that were calibrated to be real probabilities, or to match probabilities, and that had well-understood sensitivities and specificities, and that could be used at different operating settings for making predictions, different thresholds that could be set. And this could apply to whether it be readmissions or the prospect that a patient, an inpatient would have a C. diff infection within 48 hours. And you can sort of understand the sort of the trades and the predictive positive value. And most importantly, I think the methods that would generate probabilistic predictions could be coupled with decision theory along the lines of Ledley and Lusted's original manifesto to identify ideal actions under uncertainty in this data to predictions to decisions pipeline. And as an example, in the work on readmissions, which you can read about, we applied a decision theoretic analysis, almost like a decision analysis on top of the probabilities for disease-specific scenarios such as congestive heart failure, and showed how you could couple the predictions about the likelihood of readmissions with a cost-benefit analysis. And this could provide ideal thresholds for action, as well as indications of the result of using the end-to-end system in decision-making in the hospital with what we called what-if simulators that would allow exploration, for example, of different costs of interventional programs, likelihood of outcomes, and efficacies. We can sort of read off, if this was the case with this system being used, with this sensitivity and specificity, what would be the savings, in reducing readmissions and reducing total costs, even if you had to pay more for these programs for people identified as high risk under the operation of the system. So in the context of, I wanted to sort of lay that terrain out, because in the context of those methods, which had a clear basis in research on probability and utility, and as applied by Ledley and Lusted to medical reasoning, and then Gorey and Barnett, there was an inflection with the rise of a different set of methods about 15 years ago. And this inflection came from a different direction of work in statistical machine learning, neural network models. And these methods have taken us on, to an inflection point in AI that we've been riding on top of, kind of a fast-moving wave of innovation with deep neural network models for almost 15 years now. That wave has included reaching parity with humans on a number of challenging benchmarks in visual and language tasks. So about a decade ago, we started seeing the power of neural network models in healthcare applications, such like image-based diagnosis, in medicine spanning dermatology, and in radiology running at expert levels for those tasks per the benchmarks that were used. So we've been experiencing an inflection with machine learning, these neural models, over the 15 years. But let me just say that over the last 3 years, I like to say we've been riding on yet another acceleration that I like to call an inflection upon an inflection with the qualitative and quantitative capabilities we're seeing with generative AI models that show what I think even long-term AI researchers see as surprising and unexpected powers of generation, synthesis, and composition. These generative AI models, often referred to as foundation models, are showing surprising powers of that really are knocking the socks off many of us, and also the lay community. One of the first examples, the powers of generative models were demonstrated for computer programming. And this was one of the earliest commercial successes of generative AI, GitHub Copilot, which continues to generate guesses of the next portions of programming code that a software engineer may find useful. I remember when this, just a few years ago, it seems now, came to the fore. We did studies. We were very careful about making these systems safe and efficacious. We were like, again, we were very surprised at the power of GitHub Copilot. But over the last 3 years, there's been a great deal of excitement with the qualitative and quantitative capabilities we're seeing with generative models that are coming with scale. So here's the data center where GPT-4 was birthed. It's just west of Des Moines, Iowa. And in those days, this was a very big data center. It had 10,000 top-line GPUs and about 300,000 CPUs and very fast-paced networking and so on. But GPT-4, when it came out of that oven, demonstrated some emerging capabilities in language, mathematics, and programming tasks, and new abilities like learning to solve a new task from a handful of examples in a single interaction. Again, these powers of composition and abstraction and generalization came to the fore. We were surprised. My broader team, we ended up writing a paper called Sparks of Artificial General Intelligence that probed in multiple ways GPT-4 back in August through November of 2022. We were surprised by the general purpose powers, for example, showing the ability to write a proof of the infinitude of primes as a poem, or write computer programs in response to a prompt, like scrolling here without specialized training. Also impressed with the ability to see effective responses to long, detailed prompts, such as the one here, asking the model to perform a set of complex data visualization tasks. So these are actually creating animations. And much is being done now with these models and other large generative models, but there's deeper impact on the horizon. Now, from my background as an MD with a PhD in AI, and I tend to view myself as in the role of an AI researcher with an MD, I and my team took early looks at the power of the model of in this case, GPT-4, when it first came out, still was confidential in healthcare applications. I was floored by the ability to see these models solving really hard challenge problems, as posed, for example, in the section of the New England Journal of Medicine dedicated to really hard challenges, these clinical problem-solving cases. For example, in this case here, the system could take the whole article as context and generate a differential diagnosis with some commentary. We also turned to medical benchmarks, started benchmarking and building benchmarks, as well as using existing benchmarks on medical challenge problems like the U.S. medical licensing exam, USMLE, step 1, step 2, step 3, that we all took versions of, as no matter what era we're from. I guess Peter and I would probably call this the National Medical Boards Part 1 and Part 2 as medical students and as going into residency programs. And notice there was a clear jump with GPT-4 over the previous model. So you see the emergence there coming from scale. And you see here the actual numbers of the assessment, which coming in as expert levels for a 5-shot type of prompting and 0-shot, which means how many examples you put into the context. And again, to see the difference with other benchmarks that had been out there and the performance of models like this Flan Palm model at at Google, when GPT-4 hit the fan, we said this is really kind of an interesting set of outcomes here to see the power we're seeing and the jump in capabilities here. And we tracked over time. We did a paper back in 2023 on the capability of GPT-4 and medical challenge problems that really sort of pointed out what we were seeing. Beyond jumps in capabilities, we saw jumps in reliability. So for example, with the model's ability to understand and calibrate its competence. This chart here shows the predicted probability of getting an answer correct on these medical challenge problems, in this case, I think it was the USMLE data sets, and the fraction of times that problems labeled by the model as being at different levels of assigned confidence were correct. So you see the x-axis here is the mean predicted probability of questions getting it correct, I mean.
You got something to eat?
We better want to mute Scott's iPhone. and on the y-axis, we see the fraction of correct answers. Now a straight line on the diagonal would mean perfect calibration. Look how GPT 3.5 is in green, moves over up to GPT-4 in terms of calibration, almost coming on that straight line. And work has continued to advance on technologies and techniques for using even the core models. So as an example, my team pursued, well, how do you prompt these models? The original work we did on benchmarking USMLE and the mid-QA and other challenge problems was showing just how basic prompting, you are an expert clinician, here are some questions. Just basic prompting could lead to some fabulous results. We said, I wonder if we can focus the model and get it to even do better with a cascade or optimizing the prompt, a cascade of operations. So as an example, doing multiple calls, building ensembles, and also asking the machine to use machine learning itself to identify representative examples to put into its prompt. And so one of the cascaded methods we published about per its power, we called MedPrompt, because it was developed for medicine. And you can see what, sort of the MedPrompt here, it boosted results. There's a kind of different kinds of ways to look at this, but not just for medicine. We showed in law and psychology, engineering. It also was a powerful methodology, and it became quite popular in many fields to use a MedPrompt style approach. Now, over the last few months, we've now experiencing yet another wave of technology that's referred to as test time scaling. I refer people to our paper preprint from MedPrompt to 01, exploring runtime strategies for medical challenge problems and beyond. The test time scaling work I find very exciting as it harkens back to my own doctoral work, where I focus on the optimization of the control and guidance of reasoning processes on challenging healthcare problems, but more generally looking for principles of meta reasoning. With this approach, a model is trained to generate and then follow context-sensitive chains of thought, with reinforcement learning being used at sort of on top of a model to train up how the system actually generates plans to solve problems. Multiple models are being constructed now that move beyond standard pre-training to look at a phase of test time scaling, and it's interesting to see boosts now for the medical challenge problems coming to the fore. Now, I thought people would find this interesting because it's getting to be a kind of an interesting crowded terrain out there with multiple models. We're seeing the growth of these different models and different organizations training them and providing them. And I think for us, as an affiliated set of communities of researchers and leaders in biomedical informatics, healthcare delivery, biostatistics, and public health, it can be hard to stay on top of capabilities and their implications. So to give you a sense for the lay of the land and trends in the AI field, we recently put together a chart showing some models and the capabilities on the mid-QA benchmark, one of the main benchmarks used, sort of QA benchmarks. So on the y-axis and on the x-axis, on the y-axis we're showing the actual performance on mid-QA, the whole mid-QA benchmark. On the x-axis is the total cost of computing the whole benchmark. Now note that the x-axis is logarithmic. So at the right, line here, we might want to call this, for those into economics and so on, we're showing a Pareto frontier capturing the performance by cost. We actually have 3 Pareto frontiers here capturing performance by cost curves over time. On the right side, lower right, is the Pareto frontier in 2023 with GPT-4 Turbo as the best model, showing the dominance of the med-prompt approach on top of GPT-4 over here. To the left of that Pareto frontier, we see gains on the curve with GPT-4o, which is very popular now in ChatGPT, for example, with med-prompt still coming in as dominant. So to get the top performance with med-prompt back then cost hundreds of dollars to start with, and then around $100. Now at the top, we see a different line there, which is the I call this the 2025. We'll go 2023 on the right side, 2024, and now we're at the 2025 Pareto frontier with the unveiling of test time scaling with its guidance of reasoning. Now, O1 from OpenAI is in blue, those blue dots there, showing some work with ensembling, for example, as well as just a tailored prompt. But to the left, you see now the O3 Mini, which came out just recently, which can be run at low, medium, and high degrees of thinking. And there's a lot of interest and questions about DeepSeek R1. And notice where that falls on the Pareto frontier here, where we see that O3 Mini Medium does better on the MedQA benchmark and at lower prices. So it's interesting to see this, and it's to keep in mind and to watch these Pareto frontiers over time. It's going to be good to keep an eye on these Pareto curves over time and for multiple challenges, and potentially seeing these models jumping into our cell phones and into our small devices as well over time. Now, recently I joined with colleagues at Harvard and Stanford to do a deep dive across new sets of, you might say, more clinically oriented challenges with the new O1 model when it was in preview. I'd like to refer you to our preprint on archive coming along with an exuberant title, Superhuman Performance on the Reasoning Tasks of a Physician. And I just want to pull out one example here that I think is really interesting to see of the performance of O1 preview on these NEJM healer cases, where O1 at the top here, the top row, shows the performance with in terms of an R-IDEA score, which is a psychometric score capturing the quality of clinical reasoning. Notice that that O1 preview is getting 78 out of 80, a perfect score. Look at GPT-4 beneath it with more of a spread towards lower scores. But look at where attending physicians are that were in the study and residents. It gives you a sense for where things might be going with uses of AI in medicine. And I should say that beyond language-centric models, of course, we have multimodal models that are bringing together multiple types of information with a focus on imagery and language, of course, play an important role in many areas of medicine. Here's the example from a couple of years ago now of LavaMed, which was a language model just built on language that was then trained on tens of millions of figure caption pairs mined from PubMed Central full text articles, and the power that it has now to answer questions about imagery once you extend the language abilities to visual information. And we're seeing increasing sophistication and size of multimodal models like everywhere. Here's work in building a large multimodal model. It's a cross-organizational project named GigaPath, published a few months ago in Nature. And this centered on training a multimodal model with over 150,000 pathology slides, 171,000 to be perfect, to be accurate, but joined with genomic and cancer staging information. And this model shows how scale can boost performance on doing cancer subtyping, for example, and mutation prediction when just looking at the visual information in pathology slides. Just an interesting sense for where things might be going. Over the long term, I believe that these multimodal approaches could provide breakthrough methodologies for delivering what I like to refer to as ultra-personalized diagnosis, therapy design, and prediction of outcomes via building models that work at even larger scales that combine imagery, language, as well as genomic, transcriptomic, proteomic, and rich phenotypic information. So in many ways, we see these benchmarks, we see these scientific studies, and you might say these are almost like science fair projects. We haven't seen the core technologies and what opportunities for AI in medicine advancing just yet as quickly as we see, for example, the capabilities on benchmarks. So with the intriguing power we see in these experiments, and publications and studies and multimodal models, a number of questions come to mind, like how can these AI advances enhance the quality of healthcare delivery in the real world? How might these advances actually be harnessed in clinical practice? How might they change workflows and practices across specialties? How can AI technologies be used in education and evaluation? What are the risks of relying or over-relying on AI technologies? What are the influences of patient-facing AI technologies? How might AI advances be harnessed and supercharge the biosciences? And looking at that Pareto frontier across that I just showed you, that terrain over time, where is AI technology going over the next 5 years? It's funny because 5 years seemed like a very long period of time. A very short period of time in the early days of AI. We just thought, oh, maybe 10 years from now, we'll see a change in some methods that might come to the fore. So there are numerous ways to segment the space of answers to the questions we might have and the questions we might cluster. Here are 6 that I've used in focus groups actually early on with GPT-4 before it was even out. We gathered clinicians together and colleagues to look at the models and ask questions about clinical care, population health, research in clinical and basic sciences, medical education, administrative tasks, and patient and family engagement. Of course, it's just some of a larger ontology. And folks, for example, have called out, as low-hanging fruit, leveraging basic AI capabilities of both traditional and generative AI or machine learning with reducing the administrative burden on physicians. And there have been a number of articles, formal studies of, for example, how these large-scale language models can help physicians to manage the patient in basket messages, which is a growing concern of physicians. They want to answer their patients with this new channel to talking to patients directly, but they can be overwhelmed. And you look at those models, the different papers coming out with different kinds of statistics and evaluations. And we also see growing use, UW at Stanford, other places, other hospitals, NYU, Columbia, of ambient transcription via voice and summarization, building structured patient notes. Some of these are focused on specific roles, such as an example, our own health and life science team, former Nuance team, creating a special DAX copilot for nursing that helps ease the burden on nurses with capturing documentation by completing flow sheets, supported with previews and studies now underway at multiple hospital centers. But the long-term focus of AI in medicine, to the classicists that went into the field with a goal and a passion about leveraging AI to enhance the quality of medical reasoning, diagnosis, therapy planning, patient management, going back to Ledley and Lusted, has been with, how can AI help clinicians with the delivery of high-quality healthcare, including boosting the accuracy of diagnosis, for example, and the efficacy of therapy. So I worked with colleagues at Stanford, at University of Washington, and other centers to explore the handling of challenging cases. And there are many stunning examples of these capabilities. For example, here's a complex case of shortness of breath. I'm not going to dwell on this and read this right now, but physicians might want to take a quick look at this in the audience. But it's a complicated case here of a 70-year-old male with a history of coronary artery disease, congestive heart failure, COPD, and smoking, who's having an acute chronic shortness of breath for today. He's been hospitalized before. He has some dry cough, and he's having difficulty providing further history. And it's been interesting to see the power of these models to basically to take in the detailed information of the medical history, the summary, the medications the patient's on, family history, the physical exam information, and then to begin to think deeply about like what's the differential diagnosis, and just sort of work with me as a physician and what you're thinking. Not just differential diagnosis, but what are some next tests and interventions that might be done, and why. With some conditional statements that are about, if patient is found to have a pulmonary embolism, you might want to do this. If they're found to have pneumonia, they might, time for antibiotics and so on. And then sort of a plan here, admitting the patient to the hospital, monitoring, oxygenating the patient, oxygen levels, education, lifestyle, and so on. And so some more test results are coming in now of his electrocardiogram, his looking at blood gases and chest X-ray and so on. And then the system will now form an impression and plan. So saying that those results now confirm an acute pulmonary embolism with possible underlying lung cancer, superimposed COPD exacerbation, and acute decompensated heart failure. And so, and a plan for treatment here. Well, interestingly, we've explored this, and I talk more deeply about this theory of mind capability that we've seen these models have confirming as having learned from lots of their work, which is never explicit like in medical literature necessarily when it comes to like Harrison's or Robbins pathology, but this knowledge about what putting the patient in the putting the physician in the patient's shoes here. What questions might the patient have about the situation when they hear about the diagnosis? And then even asking the system, can you provide an answer on the blood clots in lungs, as well as likelihood of cancer, which might concern the patient? So with all this, we have to think deeply about the challenge of evaluation. Again, these are cases taken offline, and there's been a paucity of really great studies of putting these models in randomized controlled trials into inpatient and outpatient settings. There's been some, and we see growing studies that are getting closer and closer to the real world of clinical settings. So as an example, here's a study done by 2 academic centers in Boston a little, over a year and a half ago, with 21 attendings and 18 residents. They used, again, 20 simulated clinical cases, each with 4 sections representing sequential stages of the diagnostic and therapeutic phase of reasoning. And they had 2 measures here: diagnostic accuracy with cannot miss diagnosis inclusions, like you cannot miss this diagnosis as a measure, and correct clinical reasoning as judged by experts. And the results were for the cannot miss diagnosis was the model got 66.7% correct. The residents 66.7%, and attendings 50% on this. Residents, I guess, are more up to speed sometimes than their attendings. On incorrect clinical reasoning, the model showed this for 13.8% residents for 2.8% of the cases, and attendings at the level of the model is 12.5%. So it's interesting to see these results on this study. Now, here's another study of the value of large language models to help with diagnosis in clinical settings that I've collaborated on as a co-author, where we set up a randomized clinical trial, including 50 physicians in family medicine, internal medicine, and emergency medicine at multiple sites, including Stanford, Beth Israel, and University of Virginia. The clinicians were randomized into 2 groups, one using the conventional resources, and one using conventional plus large-scale language models, and they were given 6 challenging clinical vignettes. And the findings are very intriguing here. The LLM did not significantly enhance the diagnostic reasoning performance compared with the physicians using just conventional up-to-date and Google search, for example, conventional resources. The median diagnostic reasoning score per case was 76% for the LLM group and 74% for the conventional resources only. It was not significant. But check this out. The LLM alone demonstrated higher performance than both physician groups. So you take a look at this. I mean, so alone got 92%. So this indicates the need for technology and workforce development from my point of view. I wrote the section that, or contributed to the section talking about how can we understand this result. We need to better understand how we could mesh the output of these models and to realize the potential of the physician AI collaborative experience in clinical practice. And hold on to your seats, because we're now working on a follow-up study, co-leading right now, that takes a very different approach to how the model and physician work together. And I expect to see very different results on that. As I said here in the paper, we indicate this indicates that further development in human-computer interactions is needed to realize the potential of AI in clinical decision support systems. I think it's an important direction. Another direction is medical education. I'm going to basically leave some time today. I decided to take out one section because I want to have some Q&A time. And I won't dive into medical education, but there's so many cool directions for example, and I've presented on this in our papers, for taking a USMLE question and having a GPT-4 model convert that question into a whole interactive experience where values are changed automatically by the system and to make different multiple choice items more correct than others, doing formal differential diagnosis generation and next test ordering based on USMLE questions, and even doing rich simulations of cases, multi-day stays in the hospital with the LLM as a simulator of labs, tests, patient notes, day by day until discharge, given an inpatient setting, inpatient statement and the situation that the patient and physicians and the care team are facing. But I want to now turn to research in the clinical and basic sciences. AI R&D at the frontier of the technologies right now, as well as the expectation for what AI will bring to biomedical informatics is a really interesting frames an interesting set of questions, and also the impact on the biosciences more broadly. So first I want to just talk about the need for a synthesis. And this is in part why I started out this presentation with a reflection about the arc of AI developments over time. Here we have on the left the decades-long AI trajectory with conventional machine learning, probability and decision theory as a normative basis. And then to the right side here, we have this like generative AI disruption. And so questions are arising about the relationship of these, the disruption. Can we ever get back to this? Can we do a synthesis of some kind? And I think there are opportunities for a synthesis and integration over time. And the opportunities include harnessing LLMs for the new capabilities and using them, together with some of the classic decision-making methods. Another idea is to identify limitations and to pursue innovations at the level of making these foundation models better in certain ways. But there's the possibility of constructing integrative weaves of new kinds. Let me talk about one direction here. So remember the Octo Barnett, Tony Gorey sequential diagnostic blueprint that I put up, and we talked about how that all flows, kind of archetypal or canonical, and how reasoning works. So probability theory being used to generate differential diagnoses, utility theory being used as a way to sort of an information theory to think through, do I halt now and act under uncertainty, and what next tests might I employ? Well, how does that all might relate to a GPT model? And let me just share my experience with playing with O1 when it first came out, because I was very interested in its ability to handle, per confirmation, longer contexts in a coherent way. So I generated a prompt, a 4-page prompt. You can look at it here. I'll just blow a piece of it up here. Where I basically wanted to lay out the architecture of what sequential diagnosis with probability and decision theory does. So I laid it all out in architecture, operation, and flow, how you do updating and stopping. And it's kind of interesting, put the whole 4-page prompt into O1. It has this test time ability to reason about with chains of thought and control them. And the system says, thank you for your detailed instructions. Could you please provide the initial patient findings so we can begin the diagnostic process? So we literally, I mean, my goal here was to build one of the models that Peter and I worked on together in 1987 or 86 that can do sequential diagnosis with a prompt to a sophisticated language model. So I said, yeah, I'm seeing a 26-year-old female in the ambulatory medical clinic. She complains of an atypical headache and general malaise for 3 days. She presents with a fever of 37.7 degrees. Physical exam is unremarkable except for some slight jaundice, most notably in her sclera. The system takes this information in and it begins to build an initial differential diagnosis. What's interesting here is the system is showing me its reasoning, building out tables to show me its priors, its update of P of evidence-given disease, it's computing and renormalizing, and it's providing justifications of its final differential. And I thought I'd make it look like the old systems we built in the 80s. Show me the graph. The system is, it's part of its prompt is to show me a graph at every state, every phase here. Show me a graph of the differential and also next best test. So here's what it's coming up with probabilities, including this other category. So justifications here. And now it goes into the idea of should it halt or not or continue, and shows me the reasoning. And it goes into the evidence gathering phase now. So now it's doing cost benefit analysis in its own way. And it shows me based on its analysis of it's coming up with a list of questions I should be asking. And it puts a chart up here of the next net expected value of information, like we did in the old days in the 1980s in our systems. Please let me know which piece of information you'd like to explore further, and I will update the differential diagnosis accordingly. I said, well, patient is not taking any medications beyond ibuprofen. She doesn't consume much alcohol, had a glass or two of wine 2 weeks ago. No history of risky sexual or drug exposure. She has not had any recent travel, but she did mention this lesion we noticed a bandit on her heel and it's an inflamed scrape. She mentioned the lesion came during a hike around Surprise Lake in Fishkill, New York, when she scraped her heel on an old wooden pier. Physical exam is negative for lymphadenopathy and splenomegaly. So that information goes in natural language. And the system now goes back cycling now like we did in the old days with Octa Barnett, with our pathology systems, our trauma care systems. And it's now writing out its reasoning again, its Bayesian reasoning, its probabilities. It's updating its chart, putting leptospirosis at the top now. And now it's going to evidence gathering phase after not halting. It generates a new set of tests to do. It sorts them by net expected value or approximation of a net expected value of information. And it's asking for liver function tests, a CBC, urinalysis, leptospirosis serology, and blood cultures. Please let me know. And so I ordered the CBC as a physician, liver function tests, urinalysis, leptospirosis serology, and blood cultures. The CBC has come back showing elevated erythrocyte sedimentation rates and peripheral leukocytosis with a left shift. This is, as the medical folks out there know, this is indicates some sort of it can indicate some sort of a parasitic infection. The kidney function and the BUN and serum creatinine are elevated, and I'm waiting for the results. So the system now it's cycling again here, probability theory. It's doing its updating. showing me the posteriors. Now it's coming close to a really higher probability of leptospirosis. It's justifying, it's reasoning. It now goes into this halt analysis, and it says decisions point. Again, keep in mind, this is all from the same 4-page prompt. Stop and treat or continue gathering information. And basically it's saying, given the probabilities, as leptospirosis is potentially a severe disease that can progress rapidly, leading to serious complications like renal failure, liver failure, early treatment with antibiotics can improve the outcome. Delayed treatment may increase morbidity and mortality. Awaiting further test results may take time, and serology may not be positive at early stages. So it's reasoning about this. And the risk of misdiagnosis. It's saying, well, starting empiric treatment for leptospirosis carries minimal risk, as the antibiotics used are generally well tolerated. So, then it goes through and gives me my options here. Wait before starting treatment or treat now. It recommends I go ahead and treat now, while waiting for the other results. It gives consideration of other causes and talks about patient counseling. And here's the conclusion of its analysis. So I have to say, I was blown away by this, like blown out of the water, that I can just write a 4-page prompt. And look, we have to confirm, right, the reasoning at every single step. But the fact that the system is now writing out its reasoning is the opportunity to call tools, call calculators, call Bayesian reasoners, for example, and this provides the overall architecture and flow with some intuition about cost-benefit analysis, differential diagnosis, information value. System was I had to summarize and make sure the case is all wrapped up here. So my comment here is that when it comes to this possibility of seeking integration, we're still in early days. I think there's opportunity to do more with this. Now, I'll just mention briefly 2 other projects before concluding, and I just conclude early. I think I'd like to leave time for conversation, so I won't dive deeply into basic sciences. Just to say that there are different ways now people are using to steer, shape, and harness LLMs. There's specialist tuning, there's prompt innovation like MedPrompt, there's retrieval augmented generation where databases are attached and used by these models. And then there's the idea of like building agentic systems that actually can read, where you decompose as a problem solver into sets of prompted reasoners. They can have different capabilities as well. We have a project called AutoGen at Microsoft Research that lets people build multi-agent systems. One version of this is called Magentic 1, which has a bunch of interesting types of predefined agents. I'll just show you a system we built with Magentic 1 I call the Biomedical Research Assistant, where there's an orchestrator agent, a coder, a computer executor, a web surfer, a file surfer, and a biomedical research reviewer. And I built the system last summer with Gagan Bansal and Adam Forney. I said, I want you to collect and read relevant literature given a question, assess the scientific rigor of each paper. Let me give it some tips about how to do that. Synthesize a holistic report, identify contradictions and disputes, propose next steps forward with studies and experiments, and provide output in every single phase here. So the system actually will go out and it'll actually work and start, given a question like, for example, what is the role of telomere length in cellular aging and senescence? It'll go out and literally begin a work working directly with PubMed, figuring out how to query PubMed, and as it does that, it begins to evaluate for each paper the scientific rigor and findings, the experimental setup, the size of the clinical trial, and so on, funding sources, and builds sort of a holistic report over time, weighing the evidence, identifies contradictions and disputes, and then proposes new steps, like new experiments to do that might sort of clarify things moving into the future. Now, you can imagine in the biomedical informatics community, we might have different approaches to thinking through how to use agent-based systems. There have been several efforts, for example, right now, one at Microsoft, one at Stanford that I'm engaging with on building a system to help tumor boards. So in medical school, I found that some of the most interesting meetings were tumor board meetings where around a complex cancer case, for example, with a patient, the patient and patient's family comes and we sit with oncologist, the radiologist on imaging, the social worker, the pathologist to talk about the cells. And there's a conversation, surgeon, about what to do next and what's the best task ahead. And so these systems now are being prototyped to take as agents different expert models that might do pathology, radiology, reason about genomics and oncology, and start building out a case with a flow, adding different expert agents to the system, and having a discussion with humans in the loop, of course, the experts in the loop, with research papers being brought to the fore, different approaches to therapy, discussion points, and so on. And I think that's a really great direction to move in. But I wanted to end by talking about ethics, equity, safety, and society. And beyond the technical advances, we're going to have to attend with care to key considerations of ethics, equity, reliability, and safety, and broader socio-technical influences of AI in medicine and bioinformatics. So there's some recent and ongoing efforts that are underway, as captured in these recent publications here on the left. For example, the recent National Academy of Medicine Vital Directions report on priorities for action with AI in healthcare, published in Health Affairs just a month ago. The National Academy of Medicine Code of Conduct project that I'm involved with, on coming up with a code of, code of conduct framework for AI in healthcare and biomedical science. It's been an interesting set of discussions with a great group of colleagues. And beyond influences in healthcare delivery, there are challenges with thinking about the integration of AI into workflows, the physician's role and agency, and directions with human-AI collaboration, as I mentioned earlier. Now, also, we need to explore issues with advancing AI capabilities in the basic sciences, such as the risks of new powers of AI being used in malevolent ways, for example, posing biosecurity risks with protein design capabilities. We need to also stay on top of influences of AI capabilities on scientific research and publication. There's a National Academy study that I've been engaging with, pursuing understandings, recommendations, and putting together a standing committee to review and weigh in on risks that AI technologies pose to scientific integrity with uses of AI applications in the course of doing science. For example, special considerations to assure the veracity of inferences, replicability of results, tracking the provenance of data and ideas, and attributing sources. So with that, I wanted to summarize by saying, if folks search on AI Anthology, the set of AI essays on AI, right before GPT-4 went public, I stood up a project working with OpenAI and Microsoft to engage with leading experts, about 20 experts and influentials across multiple disciplines, to give them early access before GPT-4 was public back in 2022, and to play with it and write an essay on the possibilities for harnessing this upswing in AI technology of a certain form for human flourishing, and what would it take. And you see, quite a few essays were on healthcare-related work. And I'll just focus on Bob Wachter's essay here, where he asked in his essay, he titled it, "Will GPT-4 be the technology that finally transforms healthcare for the better? How can we ensure that physicians and other clinical personnel stay alert when the AI is correct 98% of the time? Will future versions of GPT-4, of course, we're beyond that now, be the killer app that finally allows healthcare to deliver new values, new levels of quality, safety, and equity, and improve patient and provider experiences? Will it generate efficiencies that allow our healthcare system to operate at a cost that doesn't bankrupt businesses, government, and patients?" I believe, he said, the answer will be yes, but it exceeds the capacity of this particular human to predict whether these benefits will be seen in 2 years or 20. And with that, let me just stop and take some questions. Thanks, everybody, for your attention.